I thought I would do a little video about oscilloscope probes. Recently, I received a new Regal MSO 5000 based oscilloscope, and it came with these little probes, which I am less than enamored with. Now, the interesting thing is that if you look on the internet, you will find quite a few videos by professional engineers, and when asked what to look for about oscilloscopes and so on, they say, well, make sure your probes are 1.5 times the bandwidth of your oscilloscope. And it is interesting to me that this oscilloscope, this probe here that came with the Regal, is actually rated at exactly the same bandwidth as the oscilloscope, 350 megahertz. And similarly, I've got one here from that came with the Siglent oscilloscope we used to have before, which has a bandwidth of 200 megahertz, and it also came with a probe that is rated at 200 megahertz. Now, so I decided to have a look, to experiment with these things and hook them up to a spectrum analyzer and so on, and see if I can determine what the bandwidth of these things actually is. In any case, so I went to internet, and on Amazon and on AliExpress I found a number of probes. I found this one here, which is actually a 500 megahertz probe. It only is a 10-to-1, but we'll get to that. And another thing that the reason I wanted some different probes is I like probes that have these little adapters that you can plug them into B and C connectors. And the Regal ones didn't come with that, so. And I found some strange looking probes like this one here. This is supposed to be 300 megahertz, but I just got it because it intrigued me. It's kind of like you can unplug the ground lead, but the ground lead is very long, which is usually not a good thing on oscilloscope probes, and it just has a tip. There's no ground there, so, but I thought it was cheap, so I thought let's check it out. It's a 10, again, it's a 10 mega ohm one, and 10 times at 300 megahertz. And then I got one here that I got is a P40. It's a 100 megahertz probe, but it's a 100-to-1 probe, and it can handle 2 kilovolts. So this is a high voltage probe that you can use if you're probing in high voltage circuits, but we'll talk more about that because those voltages are not necessarily correct at high frequencies. And so this is the Siglent one. I do have an old cathode ray oscilloscope from BK Precision, which was actually a cheaper one, but I still use it, especially if I want to use it, look at XY coordinates on the oscilloscope, which the digital oscilloscopes usually don't do a good job on. So this is the probe that came with that, and it doesn't tell you at all, I don't think, what it is, other than saying 600 volts peak to peak. All these probes here are actually of the passive type. There are active probes as well, and I do not have any of those. They tend to be expensive, and we are just going to be therefore talking about passive probes today. So passive probes, they do not have any semiconductors in them like amplifiers or things like that. They are called passive probes because they just have resistance and capacitance and inductance and so on. So it's also interesting to note that when you look at the bandwidths of these of the oscilloscopes and the probes, they actually quote the bandwidth of when the probe is set at 10 times, not at 1 times. At 1 time, these probes tend to have switches on them. This is a one time. This one actually has a reference position, which is actually ground, and 10 times. Many people are confused what 1 times and 10 times actually means, because at 1 times you get a signal that is 10 times greater on the oscilloscope than at 10 times. So they say, why is that so like that? Well, it is actually to do with the impedance. At 1 times you'll get the impedance of the oscilloscope, which is usually 1 megohm, and at 10 times you'll get 10 times the impedance, which is 10 megohms. So that's kind of what that's all about. And when you look at these fact sheets of these probes, this is actually, let's have a look at the one that came with the Regal oscilloscope. Let's zoom in on that. So if we look at this little document that came with the Regal probe, make it a bit bigger even, we will see that the bandwidth over here at 1 times is only 35 megahertz, and at 10 times is 350 megahertz, which bears out what I was saying about that you really have to always run your probe at 10 times if possible. The input capacitance is 50 picofarads at 1 times and 10 picofarads at 10 times. So you're starting to see why the frequency response is higher than 10 times, because the capacitive reactance of the input capacitance gets smaller and smaller in ohms wise at higher frequencies. Also, the voltage, of course, ratio, of course, goes up. These probes are actually fairly low rated, 300 volts RMS at 10 times. If you are in Europe or in Australia, and if you try to connect this to a switch mode power supply, some of it will be 400 volts or so. So that wouldn't be good. You'd have to make sure you got a special probe for that. And what else is there? Not much else to note. Now, an ideal oscilloscope probe would have no attenuation at all, would have an infinite bandwidth, and would be totally linear in phase characteristics at all frequencies. But of course, such a thing doesn't exist in the real world. The probe, when connected to the oscilloscope, forms a complex circuit. It has resistance, inductance, and capacitance. So when the probe tip actually connects with a circuit, it adds its own circuit to the circuit under test. And of course, that can affect the measurement results, and in extreme cases may actually change the circuit characteristics that you're testing enough that the returned measurements are actually invalid. For instance, an oscillator may actually change frequency, or may even stop working altogether, or maybe end up having harmonics that are normally not there. So in order to avoid that, probes are made with high resistance, and at 10 times, as you see, in DC or low frequency, the actual input resistance is 10 megohms. However, at high frequencies, this will no longer be the case, and therefore they have these little graphs here. For instance, on this particular probe, okay, and as you can see here, the input impedance, when we're talking about the 10 times 1, at even at 10 kilohertz, it starts to dip quite a bit. Somewhere between 10 kilohertz and 100 kilohertz, it actually becomes 1 megohm, and at 1 megahertz, it is actually less than 15K, and at 10 megahertz, it is maybe what, 12K, and at 100 megahertz, it is actually like maybe 500 or 600 ohms on this particular probe in a 10 times mode. Similarly, because of that too, the voltage is derated, like it is rated at 300 volts peak to peak, but even at 1 megahertz, you're really looking at like 100, and it goes down from there. At 10 megahertz to and up, it is like, I don't know, what is it, 15 volts or something like that. So, as I said, the actual probe itself actually becomes a complex circuit at at higher frequencies, and there are things like this you could think of. In the input, there is an input inductance, because any wire has inductance. There is an input capacitance, there is some resistance, and then in actual fact also the ground lead has inductance as well, which comes into play at very high frequencies. And you can see that when you look at a high frequency square wave, you might see ringing, or that the rise time is lower than what you would think. And for this reason, the probes actually have usually an adjustment on them. And this is what is being discussed in this section here. The oscilloscopes typically have a square wave output that is fairly fast rise times, and you connect the probe to that, and you would have an adjustment on the probe. On this particular one, the adjustment is on the probe body, but you will find that the faster and more expensive probes tend to have the adjustments in the actual near the B and C connector. Like this 500 megahertz one, for instance, see there's a little adjuster in there right where it connects to the scope, and there is no adjuster on the actual body itself. The Regal one here has the adjuster right here on the actual scope body, and that's probably, especially at lower frequencies, that's the more common one that you see. But that is what that is all about. Now, when you look at online, if you look at information on probes, you might find certain circuits being presented. Let me get one here. Circuits like this, which are very simplified. So you will see the probe resistance and the capacitance. Then there is the cable that has capacitance, the scope has capacitance, and of course the scope has a input impedance of usually 1 megohm, but this does not really give you a full picture of what is actually going on. It's very simplified, and even some of them give you a picture like this that's a little bit more accurate, more complex. See again the resistance, the capacitance, the probe cable, and in this particular one it's a bit like this one over here that has the compensation in the near the BNC connector that's connected to the scope. There is this one tends to have a capacitor for compensation. That may not entirely be true for some of the high level probes. And then of course you've got your scope. But in reality, what we actually have is more something like this. And to start with, this the cable that comes with the probes is actually a coaxial cable, but coaxial cable, it's not a normal coaxial cable. If you cut these apart and you'll see what's inside of them, you will find a single stranded wire that goes from the input to the output of the cable, and it is usually made of a alloy like maybe nichrome or something like that, and it has a resistance, and that's on purpose. And when you look at this cable here, it is actually a transmission line, and you might have seen sort of images like this transmission line. There's resistance, inductance, there is capacitance, and there is resistance to ground as well with through the whole line. And by adding resistance to the actual wire, the engineer that's designing the probe can actually balance the input to the output of the scope better. And interestingly enough, I actually measured the resistance at you have to do that 1 times, because at 10 times of course it would be 9 megohms higher than this. The actual wire in the cable, the Regal one, is 180 ohms, and the cable is about 120 centimeters long. The Siglent one has a very high resistance, 375 ohms, and it's 1.5 meters long. As I said, that unknown probe that came with the BK Precision oscilloscope, which is actually probably a low bandwidth one, is 98 ohms, and that old probe I got from that BWD oscilloscope that's like 40 or more years old also has a very high resistance, 345 ohms, and it's also 120 centimeters long. Of course, the longer the cable, the more losses you have, so you'll find that the high frequency probes may have a shorter cable, like 120 centimeters, 1.2 meters. Now, the thing to talk about again, to highlight, is that this input impedance here that we were talking about before, for instance, if you have a 10 times probe, of course, is what we're dealing with, at 1 hertz, the input impedance, as this little graph showed, is going to be at 10 megohms. But if you increase the frequency to 1 megahertz, a common probe, not just this one, but on average, that value may decrease to 17.4 kiloohms. And at 100 megahertz, it might only be 174 ohms. And you can imagine that if you connect 174 ohm capacitive reactance, mostly is what it is, to a circuit, that is going to affect it quite a bit. It's like putting a 174 ohms or less resistor into a circuit. Obviously, unless the circuit has a very low impedance itself, output impedance, um, it's going to be affecting it, and you will see the traces on the oscilloscope reduce considerably, and may even change in frequency. The rise times would be invalid, and so on. So this is a thing to keep in mind. And also at very high frequencies, where's this one here? Yeah, the lead, this ground lead has inductance, and of course when you use this thing in here, there's just a wire in there that goes until it ends up in a hook. It also would have impedance. So therefore, at high frequency, they tell you to remove the ground lead and to use, they provide one of these little spring things that which you place over top of the ground there, like so. I don't know if you can see that. And what you're meant to do is to touch the point that you are going to measure with this tip over here, and this wire, somehow you've got to connect with a ground point somewhere on your circuit. Now if you're probing an integrated circuit, you might be able to sort of go to the ground pin on the IC or something like that. But quite often in circuits where this is critical, the engineers might put little pads where you can connect these kind of things too. So if you're probing the circuit, that you can actually get a ground connection. And of course, the only reason is that this is very short, and you will have less inductance, so you'll get a more accurate result on your oscilloscope. And also, as a final thing about compensation, you usually get with the oscilloscope a number of these little colored rings, and you are supposed to put those on the probes so that they respond to the channel of the probe. And if you look at the modern digital oscilloscopes, like the Regal one I've got here, has got a channel 1 is yellow, channel 2 is blue, channel 3 is pink, and channel 4 is a really dark color like this. So that's channel 1, channel 2, channel 3, and channel 4. So you put these on the probes like that, and there's another one on the B and C end, like here. So when you adjust the compensation on the probe, as described over here, you must connect the correct colored probe to the correct channel and adjust it for that channel, and only use that probe on that channel if you want to see accurate results on the oscilloscope. That is something that they don't normally mention. They just say, oh well, put it on the oscilloscope and adjust it until it looks right. But each channel can be slightly different, and it is important, especially at very high frequencies. And if this oscilloscope has a bandwidth of 350 megahertz, that certainly would apply to that. So that's another thing to mention. Okay, so what we're going to do next is we're going to take these probes and I'm going to connect them to the Siglent spectrum analyzer I got there. Okay, so I've got the probe connected now, and as you can see, it's kind of got a weird little oscillations going on over there, but the 3 dB down point is at 80 megahertz, which I guess is okay for a 30 megahertz oscilloscope. Actually, let's change the frequency. I've got it going up to 1 gigahertz center point 500. I think I'll may reduce it a little bit so we can see a little bit more detail. Okay, a little bit, tiny bit more detail there, but yeah, it's still like 81 megahertz. Okay, so now let's try this weird probe here. This was cheap. We'll try this one out. Well, this one is kind of nasty. Anything but a flat response on this one. I don't think that this probe is good for much anything at all. Let's have a look. I mean, it actually peaks at 30 megahertz, and then its 3 dB down point is actually at 38 megahertz. It's supposed to be a 300 megahertz probe. Go and figure. Okay, so let's try this old Australian probe that came with a 25 megahertz oscilloscope. I think I've seen this one before. You'll be surprised. They made some pretty good equipment over there. Let me pause it while I plug it in. Okay, so that looks a lot better than that other one. Now, it does have quite a slope going up to 60 megahertz. So it looks like the top is about 20 dB. So therefore, we're looking for minus 23 dB or so for the bandwidth. Well, actually, still going up there, isn't it? I think minus 21 would. Keeps on going. 230 megahertz. 300 odd megahertz. Boom, no, it went down. I think one could say that it has a good 300 megahertz bandwidth. And with a 25 megahertz scope, go figure. Anyway, let's try some of the other ones. Okay, now let's try this probe that came with the Siglent 200 megahertz oscilloscope. I think that these probes that came with the Siglent oscilloscope, they seem to be strange, like they don't make a good contact sometimes. I think there's something not right with them. But let's have a look. Okay, well, it's not too bad, but this one behaves differently at 3 megahertz. It has minus 13 dB. One could argue that that's not very good, that it has better response at a lower frequency than, because really if you take this to be the reference point, then when we get to -17, that would be the bandwidth, which is here. That's only 65 megahertz. But if you take the -18 to be the reference point, it seems to go forever at the same. A dip here. So that's kind of like a strange curve too. But it is quite flat at higher frequencies. From about 80 megahertz or so onwards. Doesn't change much. Okay, so this probe here also has a dip at the beginning. So where this kink is over there, is roughly the bandwidth, I think. What, 396 megahertz, so it's supposed to be 350, so it's close to 400. I guess that is what it is. But still, it actually picks up after that, and it flattens out, so you'd definitely be able to see signals beyond 300 and beyond 400 megahertz on this probe as well. Okay, so I'm not 100% sure how valid that information is. But I think there is some relevance there, because the spectrum analyzer with the tracking generator, it outputs different frequencies, and it tells you the response, how much signal it is losing, and so on. All the probes were set to 10 times, so they therefore can be compared to each other. So I think what we've learned is that the probes that came with the Rigel oscilloscope are not bad. That old probe that I have from that little 25 megahertz oscilloscope is also not bad, surprisingly. And some of these Chinese ones, the 500 megahertz one is okay, but the other one's a piece of junk. The 500 megahertz one I got from Amazon, I think. Yeah, that's the one here. Group C8SEN 500 mega oscilloscope clip probe, high precision with adjustable accessory kit. Not quite as good as the one that came with the oscilloscope, probably, but it does have the adapter for the BNC connector there, which I was coveting, and it's okay. It will do. Okay, so I have got the Rigel oscilloscope set up over here, and I'm actually using the internal function generator that it has, and I have selected a 10 megahertz square wave. So if you look at the blue trace on the oscilloscope, that is using one of the included Regal probes, which has been properly compensated on channel 2, which is actually blue. On channel 1 I have compensated the other probes, except this one over here, the BK Precision one, is actually compensated on this oscilloscope here, but I believe it is actually not that far off, but nevertheless, let's plug it in. And as you can see, when you have different probes, this particular probe, of course, it came with a 30 megahertz oscilloscope, and when we put it on the spectrum analyzer, we saw that it didn't have great specs at higher frequencies. So the yellow trace is actually somehow delayed, and the amplitude would depend on the actual internal resistance. I've got them set for 10 times, so they're supposed to have 9 megohms resistance, but they will vary just a little bit, and you will get different amplitudes. But nevertheless, you can see that the waveform has a little bit more ringing, and it is out of phase somehow. So let's try another one. So this is actually showing that if you're using a probe that is inappropriate for your oscilloscope and also for the frequencies that you're working with, you might see quite different results than what you would expect. Now next, let's try this strange blue probe. It didn't have very good specifications on the spectrum analyzer. It is supposed to be a 300 megahertz probe, but we saw that there were dips there after 85 megahertz. But at 10 megahertz for the square wave, you may not necessarily exactly see. Oops. Did you see that? It tried to escape. Let's plug this in first. Oops. So this one is actually better than the other two, as you can see, but still the amplitude is a little bit different, and it has a little bit more ringing, I suppose. If you change the time base, you kind of see what we're talking about. Again, this was not a great probe, and it was made for a different oscilloscope. Put that one aside. Okay, the last one, we'll try this supposedly 500 megahertz probe. I think this one didn't do too bad on the spectrum analyzer. Angle the wires here. This one has been properly set up for this oscilloscope. Oh, unplug this one. And yes, as you can see, there's slight difference in amplitude, but there is fairly close to the Regal probe. And we're presuming that the Regal probe is actually correct because it was made for this oscilloscope and so on, and hopefully the engineers at Regal did their homework and made it work properly on this oscilloscope. So I thought that was interesting, and there's just a slight difference in amplitude, maybe a little bit more. Seems to lag just a teeny weeny bit from the Regal one. You know, it's not bad. It's pretty close, I think. Yeah. So that's about it. So that's all I've got. Been an interesting little experiment with oscilloscope probes. I did have a look online and I saw a thing on the Keysight website where they were saying, oh, if you've got this kind of oscilloscope, it's got a pulse generator, and it was like 2 pages full of instructions how you can actually measure the bandwidth of a oscilloscope probe. I don't have such facilities, and it all sounded very complex. And I'm thinking that the spectrum analyzer does show which probes have certain characteristics. May not be entirely perfect, but it was an interesting experiment, and I hope you got something out of it. I think that's all I've got. If you like, subscribe and all that sort of stuff, as they say, and I'll see you next time.